I'm Rafael de Cabo. I work at the National Institute on Aging, and I lead the Translational Gerontology branch. Our lab is split in between 3 centers. So we are in this tall building in Bayview campus, across the bay in Bayview Hospital, and in Harbor View Hospital, and then in the Animal Center where we have our non-human primates. I'm going to give you a brief intro of what the Translational Gerontology branch, the goals that after meeting the PIs with Luigi Ferrucci, Stefanie Studensky, Nigel Gregg, Isabel Bierman, we came up with the list of things that we wanted to study. But basically what we did is take advantage of these conceptual domains of the hallmarks of aging and put them in the context of the domains of the aging phenotype, and trying to find and identify how some of these hallmarks of aging are the underlying causes of some of these underlying causes of the domains of the aging phenotype, like changes in the body composition, energy imbalance and production, homeostatic dysregulation, and neurodegeneration. And how can we intervene through either nutritional, genetic, or environmental interventions to affect and change the outcomes of the aging process. Just to keep chiming on the whole theme of the meeting, is aging is a process that affects all of us, and the whole entire world population is getting older. By the year 2050, you can see that lots of the old world are already in deep problem with 30 or more % of the population over the ages of 65. So that is going to be has a tremendous impact both in the society and also in the socioeconomicals of most of these countries. So Felipe showed this slide, and again, aging is the major risk factor for all chronic diseases, and I think that the only thing that you need to do to accumulate 1, 2, or multiple of these diseases is to get old enough. And then with the passage of time, you will undoubtedly get one of these, and those will be determined by your nutrition, your genetics, and the environment. One important point is that we do not age at the same rates. Males and females, women and men do not die with the same diseases, do not age at the same rate, and the diseases of aging and the chronic diseases are not evenly spread across sexes. Another important concept here is that no matter what you do, you cannot stop time. So time, it will progress regardless of what you do. But we know that there are interventions that we can do to sort of slow down a little bit the aging process. So we always get asked the question, can we really stop aging? Can we stop the process of being young and beautiful to be old and beautiful? And the answer is simple, is no. There's nothing that we can do to slow down, to stop the aging process. There are things that we can do to slow this process down. And importantly, we can also manipulate this process. I'm going to give you some examples of this. So a concept that has been mentioned are the difference between health span and lifespan. And I was drawing last night, timing health and time. You can see that you have 2 possibilities. You have a population that is aging, and at the initial steps of life, everybody's healthy. There's very little frailty. This frailty gets the onset later in life, and towards the end of life, you get this increase of disability. And when you do interventions like caloric restriction, rapamycin that was discussed earlier, what you do normally get is an increase on lifespan. So it's just postponing the onset and the progression of some of these diseases. Plan B is when you have exactly the same type of curve, but you can see that we have pushed this to the right. So this will be an increase in health span. So there is no real changes in maximum lifespan, but what you do here is like a compression of morbidity and mortality. And then what you get is super healthy old people that die in a very short period of time. And this will be, the example of an unsuccessful aging. This is an Indian woman from the desert of Arizona, probably had a poor nutrition, has a completely different genetic makeup, and it has been exposed to the environment and the sun all her entire life. And then you have this Zen monk from the Himalayas that, at the age of 91, I hope I look like that when I'm 91, I'm as small as bald, but that will be an example of optimal aging. That's something that you can, search or trying to mimic in the end. The one thing that we have also mentioned through the conference is the heterogeneity of this process, and this is super important. We have been looking at lifespan curves and how this lifespan curve can be modified to shorten or to extend lifespan. And it's important that we've been talking also about genetic heterogeneity, genetic homogeneity in comparing humans and mice. And what I want to tell you is that even mice that the C57 Black 6 male mice, these are the standard workhorse in aging field. These are 2 years old, and we got 400 mice, and you can see the heterogeneity of the phenotype, a simple phenotype like his body weight. You have a tremendous heterogeneity of the population, and things like functional outcomes like grip strength, there's also tremendous heterogeneity. So if you compare this heterogeneity to human heterogeneity, and this is data from the BLSA, this is males on the BLSA, you can see the huge also heterogeneity on body weight and also grip strength. So you have a genetically heterogeneous population, humans, compared to a mouse that is homogeneous genetically, but the phenotypes of aging are equally heterogeneous. So genetically, very, very different, and phenotypically completely similar. Now, the other thing is when you do treatments and when you do responses to interventions, Linda showed some of the data this morning, we're finding out that interventions that affect the aging process, rapamycin, acarbose, resveratrol, are very much context dependent. What I mean by context is that sometimes males respond better than females, sometimes it's the other way around. Sometimes to see the effect of the intervention, you have to have the animals either in calorie restriction or in a high-fat diet. So the concept that all strains and all mice and all organisms are going to respond equally well to an intervention is something that I think that we need to delete from our minds. So you can have interventions that shorten lifespan, you can have interventions that extend lifespan, but also you can have interventions done in the same laboratory when ideally, when you do an intervention, you may have a dose response, and that is great. But you can also have interventions that give you a result like this, where you have a dose response in some parts of the curve and not in all of them. And these are genetically homogeneous mice in the same lab, treated with the same thing. So why you have a subset of the population that are responding differently than the other subset of the population? Are they genetically determined? Are the positioning in the uterus what is determining the outcome? So I think that these are things that we can and we need to start thinking on exploiting with the new technologies. So this is a slide from Luigi Ferrucci, and basically, I think that the longitudinal studies and neuroscience is like a perfect marriage. I think that one of the things that we have been doing in the biology of aging is a lot of cross-sectional and comparison of 1 or 2 time points and trying to get conclusions of what will happen in the long term on any given intervention. And I think that what we need to do in the biology of aging is copy a little bit of what has been done in the epidemiology and do longitudinal studies of aging in which you do an assessment on both the phenotypes of aging and functional outcomes of aging. So you can measure the biology of aging, and as you progress in time, initially you have areas of full compensation. So when we are young and we're born, you can challenge the organism and you can adapt to the environment rather quickly. As life progresses, you lose this ability to adapt and you get less and less of a phenotypic, you get more and more of a phenotypic heterogeneity. When you get to your 60s, there's more, and when you get late in life, there's even greater phenotypic heterogeneity. And as you move to the right, you have a loss of resilience, a loss of the tolerance of the organism to resist any kind of insult. And I think that it will be awesome to see what happened with the centenarians. Do the centenarians, the people that look extreme long life, are they phenotypically diverse, or they have also like a selective phenotypes that ensures their survival? So I think that in terms of where we go next, I think that we need to start looking at the organisms, and besides the, the traditional basic science to drug discovery, animal models, human studies, and clinical trials, I think that we need to start doing what a lot of people is doing in this room, is multiomics. But I think that now that is almost like a thing of the past, and that just started like about 5 years ago. Now we're talking about artificial intelligence and machine learning, and I think that integrating all the data that we're being able to accumulate, both from the mouse world and the cell culture world, plus the human studies, I think that's where the future is laying. I think this is what we were very recently, like about 15, 20 years ago. We always got really excited when we were able to repeat the experiment of calorie restriction, that we made the animals live longer. You fast forward 10 years, and now we had Linda this morning talking about drug combinations, so things that have already extended lifespan of aspects of health span. So I think that we are here now, but I think very soon we're going to get here. So I think that this progression is happening rather quickly, and I think that we need to make sure that we don't give any missteps that can derail the whole entire neuroscience train. And I think that my hope is towards the end of the conference, I hope that everybody here comes out saying, hey, we need to refocus, we need to really rethink the way that we're doing the science to really embrace the concept of neuroscience and how we can implement it to our animal models. And I think that the following speakers, Ross, Jerry Consenti, and Darren Becker, are some of these people that really kick the, like in a football team among 5 years old. There's the ball, there's like the 22 of them, then somebody kicks the ball, and all the kids move to that way. So I think that each one of them, in their own field, have been people that have thought about the box, and I think that there are people that have been able to apply the system biology and integrated physiology to really move the field forward. So without more delay, we're going to go and continue. The next person up is Rosalind Anderson. Then we will have Darren Baker, Jerry Carcenti, and then we'll have at the very end, like we did at the first session, Q&A portion.